right, let's head on into sections 4-7, where we're going to be looking at limits again in a different way. When we did limits in chapter 2, there were all kinds of different techniques that we used to determine a limit, but we did not get all of those ways. So, the study of limits in chapter 2 was thorough, but not exhaustive. Some limits called indeterminate forms cannot generally be evaluated using the techniques that we learned in chapter 2. So, therefore, we need another tool in our toolbox to evaluate these limits, and that is going to be with L'Hopital's rule. And that's how you say it. So, what are the indeterminate forms that we're talking about? That is, if you get a 0 over 0, obviously, that's not going to give us an answer. We refer to that as an indeterminate form. What if we also get infinity over infinity? That's not going to give me one single answer, so that is an indeterminate form. If I do 0 times infinity, infinity isn't totally a number, so we can't ever reach that. Times 0, yes, should be 0, but not always. And then here, if I do infinity minus infinity, those are what we refer to as the indeterminate form. And these are the things that you get whenever you plug in the a value, the value that x is approaching, into the limit. So let's define what L'Hopital's rule is. L'Hopital's rule for the indeterminate form of 0 over 0. So, suppose that f and g are differentiable on an open interval I that contains a with g prime of x not equal to 0 on that interval. And you'll know why here in just a minute, why we have to have that when x is not equal to a. Now, if the limit as x approaches a of f of x equals the limit as x approaches a of g of x, both of those are equal to 0, then L'Hopital's rule says this. We're going to be dealing with a lot of quotient functions here. The limit as x approaches a of f of x over g of x, and this is why, actually it doesn't say g of x is not equal to 0, g prime of x. Hang on, let me write this next rule. Then we'll talk about why we have this condition. The limit as x approaches a is going to be found for this limit by taking the derivative of the top function separate by taking the derivative of the bottom function, and then plug in a. If you get an answer, then you're fine, you can move on. If you get another indeterminate form, then you might have to do this more than once. Now, this is provided that the limit on the right exists, or is plus or minus infinity. And this rule not only applies as x approaches a, but it can be replaced by x approaching plus or minus infinity, x approaching a from the right, x approaching a from the left. So, the reason I have to have this condition is that this, we don't want to equal 0, okay? Alright, so basically what you're happening is if you throw in a into f, throw in a into g, you get 0 over 0. We can take the derivative of these individually and try it again and see if we get a value. So for instance, let's look at this first example. If I plug 1 in here, 1 cubed is 1, plus 1 squared is 1, minus 2 times 1 gives me a 0 on top. All over, 1 in the denominator also gives me a 0. So this is one of those 0 over 0 forms. So, by L'Hopital's rule, it says that the limit of this is equal to the limit of its derivatives. So I'm going to take the limit as x approaches 1, take the derivative of just that function separately, then this function. So the derivative of the numerator is 3x squared plus 2x minus 2. The derivative of the denominator is just a 1. Now this is going to tell me I'm not going to get this 0 over 0 again because this can never change. So now when I plug 1 into each one of those x values there, I get 3 times 1 squared plus 2 times 1 minus 2, and you can do this in your head if you want, all over 1. This gives me a 3 plus 2, which is 5, minus 2 is a 3 over 1, which is just a 3. And that is the limit of that rational function as x approaches 1. Now, if I try to plug in 0 into here, what kind of situation do I get? That is the first rule of limits, is to plug a in. Well, when I get 0 into here, that term is gone, so I get the square root of 9 minus 3, which is 0. all over 0, so I do have a 0 over 0 case. I'm going to take the derivative of the top and the derivative of the bottom. So the limit as x goes to 0 of, now you may want to write this as 9 plus 3x to the 1/2 just so that you have that. So we can do a chain rule on the top. I'm going to bring the power out front, decrease that power by 1, and chain rule the inside. So I do need a 3 there. The derivative of minus 3 is 0, and then I have to take the derivative of the bottom, which is 1. So when I have a 1 in the bottom, it doesn't really matter. I'm going to just plug 0 in for x and figure out what my answer is. Now I'm going to clean this up a little bit. This 3 and 1/2 I can write as 3/2 times 9 plus 3 times 0 to the minus 1/2. Okay, so this is gone, but remember that minus 1/2 actually goes to the bottom, and is with the 1/2 power is actually the square root. So I'm going to write this as 3 over 2 square roots of 9. There's lots of different ways to get this. This is actually a 3 that I can cancel with that 3 and leaves me with an answer of 1/2. So the limit as we approach 0 of this radical function is going to be 1/2. All right. May happen that the second derivative also yields an indeterminate form. In this case, L'Hopital's rule may have to be applied a second or a third time. So let's do some in trig. Trig, secant of 0. Now secant is 1 over cosine. At x equaling 0, here's my 0 degrees. I have the point 1, 0. Remember, this is cosine and this is sine. So if this is 1 over cosine, then 1 over the cosine of 0, which is 1. 1 over 1 is 1. Minus 1 is 0 on top. And when I plug 0 in here and square it, I get 0 as well. So this is a 0 over 0 case. So if you're unsure on your trig stuff, please make sure you practice some of those with those special angles. All right. So let's take the derivative of the top and the derivative of the bottom. So the derivative of secant is secant tangent. The derivative of the bottom is a 2x, and I'm going to try to plug 0 in. Well, we just talked about this. This was equal to 1. Times, what is the tangent of 0? Well, the tangent is the same as sine over cosine. Well, this is the point at 0 degrees. So if I do sine over cosine, that is 0 over 1, which is 0. So 0 times anything is 0 still. If I plug 0 down here, I get 0 again. This, I have indeterminate forms twice, therefore I must do this again. So I'm going to now take the derivative of the top and take the derivative of the bottom one more time. So I need a product rule on the top. I'm going to take the first times the derivative of the second, which is tangent. So the derivative of tangent is secant squared, plus the second times the derivative of the first. Well, we already know what the derivative of the first was. It's secant tangent all over the derivative of the denominator, which is 2. Well, I now know definitely I'm not going to get an indeterminate form again because of the 2. Well, what happens when I plug 0 in? Now I'm going to clean that up a little bit in the top as I do this. This becomes secant cubed, so I need to do secant of 0 cubed plus, I need to plug 0 in here, and I have secant of 0, and I have 2 tangents, so I have tangent of 0 squared all over 2. Now, if you followed all along, secant of 0 was 1, so this is going to be 1 cubed, which is 1, plus this is 1, but the tangent of 0, we said a while ago, was 0. So 1 times 0, that's going to be a 0 over 2. Therefore, my final answer here is a 1/2. Okay? All right, so that one's a little bit more challenging because it's not a nice smooth polynomial like what we have in this next example that we must end up doing multiple times. Okay, so this one is going to take the derivative of the top, the derivative of the bottom, because when I plug 0 in here, what do I get? I'm going to get, oh wait, whoa, sorry, I have a mistake here. This should be a 2. So let's try that again. If I put 2 in there, typo on this set. So if I put 2 in there, 2 cubed is 8 minus 3 times 2 squared plus 4. This becomes a 0 because 8 minus 12 is negative 4 plus 4 is 0 over. If I put 2 in the bottom, I get 16 minus 32, which gives me negative 16, plus 28 gives me a positive 8, minus a 24 gives me a negative 12, and then we add over, I'm off somewhere, 32, 28. So that does give me a 0 in the bottom whenever I think I've said a wrong number possibly. But you do get 0 in the bottom. And so when I take the derivative of the top, this gives me a 3x squared minus a 6x plus, whoops, not plus anything because that's just a 0 when I take the derivative of a constant. So let's go 3x squared minus 6x all over. This derivative in the bottom becomes a 4x cubed minus a 12x squared plus a 14x minus a 12. And if I throw 2 in the top, 2 squared is 4 times 3 is 12 minus 6 times 2 is 12. So that gives me a 0 over. And if we look in the bottom, plugging in a 2, that gives me a 32 minus a 48 plus a 28 minus a 12 also gives you a 0. So that means by L'Hopital's, I have to do it again. I have to do it with the limit now as x approaches 2 of taking the derivative gives me a 6x minus 6 all over. Taking the derivative here is a 12x squared minus a 24x plus a 14. Derivative of negative 12 is 0. And now again we try to plug a in. So I do 6 times 2 minus 6, which is 12 minus 6, which gives me 6. All over, put 2 in here, squared is 4 times 12 is 48 minus, this gives me 2 in there, gives me 48 also, plus 14. These cancel, leave me with the 14, but my final answer is not that because I can reduce it by 2 and give me 3/7. So that would be the limit for this problem. So there's other ways to do these problems. We had factoring, we had rationalizing, we had limits at infinity, which we're going to get to. But remember, sometimes here with this L'Hopital's rule, it's nice and slick to be able to get an answer pretty quickly. So, all right, so let's try the next situation for an indeterminate form, which would be infinity over infinity. And this is going to look very similar, except for this piece right here. So suppose that f and g are differentiable on an open interval I containing a with g prime of x not equal to 0 on our interval I when x is not equal to a. Remember, we're just approaching that a when we're talking limits. We're not equal to. So the limit as x approaches a of f of x can equal plus or minus infinity, and the limit as x approaches a of g of x can be plus or minus infinity. If those two things go to infinity over infinity or a negative infinity over positive infinity, then the limit of a rational function f of x over g of x as x goes to a is equal to the limit as x goes to a of f prime of x over g prime of x. Again, taking the derivative of those functions simply as one on top and one on bottom. So provided that our limit exists or that it's equal to plus or minus infinity, and our rule is if we approach a, then it can also be the same rule for as I approach plus or minus infinity, as I approach a from the right, and as I approach a from the left. So this still holds true if I have any of these down here. Okay, so let's evaluate this function. Notice this time we have infinite limits here, okay? And we'll talk about that one in just a second. So if I try to plug in infinity, I would get an infinity on top and an infinity on bottom. So we have to take the limit now as x approaches infinity and do L'Hopital's rule to determine what our limit is. Now, what we did before was we divided by the highest power in the denominator and we got rid of those x cubes, and anything that had an x in the denominator went to 0 before. Okay, so we've done these type of limits before. This is just another tool. Take the derivative of here, gives me 12x squared minus 6x and then a 0 all over a 6x squared minus a 10x. If I try to plug in infinity, again I get infinity over infinity. So I must do it again. The limit as we approach infinity, take the derivative is 24x minus 6 all over 12x minus 10. If I plug infinity in here, multiply by anything and subtract anything, I'm still at a very, very large number. Likewise on the bottom. So I must do that one more time. So the limit as x approaches infinity, take the derivative of this is 24. The derivative of the bottom is 12. And now I have a limit of a constant, which is defined to be that constant. So this is equal to 24 over 12, which I can reduce that to 2. Okay? All right, let's try the next one to include some trig. And it's actually a chain rule that is going to be incorporated here because I have a composition of two functions. So if I plug 0 in, and I'm going to do that from the right, okay? And so I want to plug that 0 in, and if you were to graph cotangent, you're going to know that here at 0 and here at pi, you're going to have a graph. This is going to be at pi over 2. And so you're going to be able to figure out some of those values, knowing that as you approach 0 from the right, I'm at positive infinity. And then here you're going to negative infinity. So let's plug 0 into here and see what I get. When I plug that in, I get 1 minus cotangent of 0 over cotangent of 0. Well, if I plug that in here, actually 1 minus, this is at infinity, so 1 minus infinity is actually a negative infinity over by itself, as I approach 0 from the right, is an infinity, positive. So I can use L'Hopital's on this. So I need to take the derivative of the top and the derivative of the bottom. Now the bottom one is pretty easy as long as you remember what the derivative of cotangent is. If you have to look, pause the screencast and you can go look, but that is actually the negative cosecant squared of x. And on the top, the derivative of 1 is easy because it's 0, but for this chain rule, I have to take the derivative of the outside function in terms of this function, then take the derivative of this. So the derivative of cotangent again is negative cosecant. So that negative, two negatives make a positive, so I would get positive cosecant squared of the sine of x. But then I have to chain rule the inside, which gives me a cosine of x because that's the derivative of sine. Now, I'm going to simplify this, and the way that I'm going to simplify this, and there are lots of ways to do this, this is just one way that I wanted to show you because there are some tricks of the trade when you're dealing with trig functions. So, cosecant is the same as 1 over sine. So if I have cosecant squared, I kind of might want to do things in terms of sines and cosines. So I'm going to, if this is 1 over sine, I could kind of flip it to the top, and this one is also 1 over sine squared of that sine of x. I can flip it to the bottom. So I'm going to take this up to the top and make it negative sine squared of x times that cosine. And I'm going to bring this guy to the bottom and make it a sine squared of the sine of x. Now, this is one that when you plug 0 in for sine, plugging 0 in for sine is going to be 0. So this is 0 and this is 0. So this is a situation where I have 0 over 0. So I must do L'Hopital's rule again. Now, in order for me to do L'Hopital's rule again, I'm going to kind of split some of these up. Okay, again, these are some tricks of the trade. The way that you do it one time may not be the same. Now this cosine is over here by itself with all these signs. Notice I have a square and a square. So I'm going to kind of extract out Let's go ahead and take the negative out front, and I'm going to do the sine of x on top all over the sine of x. I know that looks kind of funky, but I have 2 here and 2 here, so I'm going to create that quantity squared on the outside. Then I'm going to times by, I'm going to bring this by our rules of limits. We can do this where I just now take the limit of just that function. Now, why do I do that? The reason I do that is because this piece right here is equal to 1. When I throw cosine in, the cosine of 0 is 1. So this whole limit is 1. I can get rid of it, which is very, very nice. Now we have to turn our attention back here to these two problems, or these problems, okay? What I want to do is, again, if I throw 0 in here, I'm going to get 0 over 0, so I can do L'Hopital's rule again. I'm going to actually choose to take the negative out front. And I'm actually going to, because of the law of limits, you can actually kind of bring this limit on the inside and just work with this inside function and then square the answer that you get. Okay? So, sine of x all over the sine of x, quantity squared. So this is kind of the form that I'm going to use in order to take L'Hopital's rule of this now. So taking the derivative of the top and the derivative of the bottom. So we're going to go limit as x approaches 0 from the right. I forgot that parenthesis. Take the derivative of sine gives me cosine. The derivative of the bottom means I have to take the derivative of this sine in terms of that sine, then take the derivative of the inside function of sine. So we would get the cosine of the sine of x, but then take the derivative of the inside, which is actually a cosine of x, and that whole thing is squared. Now, why is that nice? Well, obviously, these two things are the exact same thing. So I can cancel them, and I'm basically left with the opposite of the limit as x approaches 0 from the right of 1 over cosine of the sine of x. And I'm going to take that whole thing and square it. And now's the time that I can plug 0 in order to find my answer. When I plug 0 in for sine, sine is 0 at 0. Therefore, I get 1 over cosine of 0, which cosine of 0 is 1. So basically, I get the negative of 1 over 1 quantity squared, which in the end comes out to be negative 1. And that is a really, really tedious problem, but one for you to see and one that is good for you to do to keep up on some of those trig identities and trig functions, okay? All right, very good. Let's move on to our last two indeterminate forms, one being 0 times infinity and the other one being infinity minus infinity. Therefore, sometimes functions have to be finagled in order to be able to use L'Hopital's rule. So we are going to evaluate these following functions. Now notice I have a product where if I plug infinity in, this is going to be infinity, but when I throw infinity here, 1 over infinity is 0, sine of 0 is 0. So here's the 0 times infinity. Okay, maybe I should do infinity times 0 because that's kind of the order that we have. So infinity for the x squared times 0 for the sine of that. All right, now in order to do this, we want to create a rational function to be able to use L'Hopital's rule. And a nice slick way is to focus on this piece right here. Now, we kind of did this up here in this function right here where I took the cosecant, which was 1 over sine, and kind of flipped it to the bottom and made it into sine. And this was negative cosecant squared, which is 1 over sine squared, and I can flip that with the reciprocal to bring it up top. That's kind of the idea that we're going to work with this x squared. If I were to change this, x squared is equal to 1 over x squared. So if I did 1 over this, I'm asking for the reciprocal of this fraction, which comes back to this x squared. So what I'm going to do is kind of basically flip this to the bottom and make it 1 over x squared. So I get this, the limit as x goes to infinity of the sine of 1 over 4x squared all over 1 over x squared. And so that, if I end up plugging infinity in, we just talked about that up here, this is 0 over. 1 over infinity also is 0, so I need to use L'Hopital's rule in order to eliminate that indeterminate form. So I'm going to take the derivative of the trig function, which is going to be cosine of the 1 over 4x squared, but I also have to chain rule the inside. Now, what is that equal to? 1 over 4x squared, here's what we're going to look at it as. 1/4, and I'm going to bring that negative power in as x to the minus 2. So I'm going to do a power rule on this. Bring the 2 out front, gives me negative 2/4, which is actually the same as negative 1/2. And decrease that power by 1 gives me x to the minus 3. All over, taking the derivative of this, now I'm just going to write that as x to the minus 2. There's no extra number in there, so I'm going to bring the 2 out front as a negative 2. Decrease that power by 1 gives me a negative 3, which is very, very, very nice that we have this chain rule piece, because this now goes away with that. And now I can evaluate my limit in the top. What does that become? Well, that becomes infinity on the bottom. 1 over infinity approaches 0. What is the cosine of 0? It is 1 times negative 1/2 all over this negative 2. Well, I can get rid of my negatives if I want, because they change to a positive, and I get 1/2 multiplied by the reciprocal of 2, which is 1/2. Final answer is 1/4 for this problem. Okay, or if you so choose to do extremes over means, when you have negative 1/2 over negative 2, you can do your extremes over means and still get 1/4. Okay? All right, very good. Now, our last problem here is a little bit different than what we've seen before. We're going to do kind of a change in variables here. If I throw infinity in, this is going to infinity, and if I throw infinity in, it's still also going to go to infinity, so this is one of these infinity minus infinity cases. And so we again have to form a quotient. Well, here's where that's going to be tricky. We want to take out this highest power here. We're going to create a fraction within here. And so I'm not going to do anything with that x yet. My goal is to kind of get an x out here in front of this radical, so that I can kind of factor out an x out front and do kind of what I did over here, where I can flip it to the bottom. Again, we have to form a quotient or a radical. So in order to get an x out front, I have to have underneath my radical an x squared. So that is what I want to factor out of that binomial underneath. Well, if I factor out an x squared, what do I multiply x squared by to get an x squared? It is a 1. Now, if I take 2 x's away when I only have 1, that means I'm going to have 1 in the denominator. So x squared times what gives me 3x? It is 3 over x, and that's kind of the tricky part there as well. Now, when I do that, now this allows me to have that x squared that I can bring out front in terms of just an x. So I end up with x minus x square roots of the 1 minus 3 over x. Now, this is the place I'm going to factor out an x, so this gives me the limit as x goes to infinity. Take out an x, and I'm going to be left with 1 minus the square root, and here's where I'm going to change this to get my negative exponent. You can do that along the way, wherever you choose to do it. I just know I'm getting ready to take a derivative, so that's going to help me out. All right, so I'm going to now do this trick, where I'm going to take this x squared and I'm going to bring it to the bottom and make a fraction. So I get the limit as x approaches infinity of all of this. Now I'm going to go one step further in order for me to prep to do a derivative. I'm going to write that as a 1/2 power for that radical, all over. Bringing this guy down ends up with a 1 over x. Okay? Now, let's now take the derivative. Because when I throw infinity in here, I'm going to get 1 minus 1, which is 0. Throw infinity in here, I get 0. And so I have a 0 over 0 case. So here we go. When I take the derivative of the top, actually, hang tight. We're not going to take the derivative of the top. We're going to do kind of a change of variables thing. I'm sorry. I should have looked at my notes. All right, so it would be this is kind of a technique that we use in some instances. You could actually take the derivative of these. It's going to be pretty nasty, actually, in a chain rule sense. But it can be done, okay? So I'm going to actually do a change in variables here. I'll show you this way because it's a different way. I'm going to let that change in variable be equivalent to this 1 over x, and I'm going to call it t. T is going to be equal to 1 over x. So I can actually change my values here. Okay, so let's rewrite this back into, maybe I shouldn't have changed all of that. I'm going to rewrite it as 1 minus 3 over x to the 1/2 all over 1 over x. Now, if I'm changing variables, then all these x's have to turn into t's somehow, and then I'm going to take the function and evaluate it at t in terms of t. So the limit as t goes to what? Now, if I let infinity be the x, 1 over infinity goes to 0. Now, since we're going to positive infinity, I'm going to change that to 0 from the right because I'm looking at positive values here. Now, I'm going to have this one, nothing changes there, minus that one doesn't change. But now if I have 3 over x and I let t equal 1 over x, well, 3 over x is the same as 3 times 1 over x. There's my t value. So I'm going to write this as 3t to the 1/2 power all over. This is what I allowed t to be. So now we don't have to worry about working in negative exponents. Again, you can take the derivative of here. It'll be very similar to what we did over here where you could cancel some things out. But this is another way to kind of work through that. So when I plug in 0, that again gives me 0. 1 minus 1 is going to be 0 over 0. So we have to do L'Hopital's in terms of t this time. So I'm going to take the derivative of the top. This is 0. Let's bring our 1/2 out front. So I get a negative 1/2 times that 1 minus 3t. Decrease that power by 1, which is negative 1/2. Chain rule the inside, which gives me a negative 3, all over the derivative of the bottom, which is 1. And so I get to now, you don't have to worry about this. I'm going to put these two together as a 3/2, and I'm going to plug in 0. Well, 0 goes away, so I get 1 to the negative 1/2. Well, it's very nice that 1 to any power is going to be 1. Therefore, my final answer here is 3/2, and that is our final problem for this section. So I know those last two can kind of get a little bit tedious. Again, you don't have to do this change of variables. If that confuses you, you definitely can do exactly what we did over here on this side in order to find your final answer as well. It'll all end up being the same, okay? All right, so this is just another look, another tool for limits that is kind of isolated in its own little section here in Chapter 4. Our next section that we're going to is Section 4.9, which is dealing with antiderivatives, which is going to be so important to what we do in Chapter 5. So until next time.